And welcome to Chapter 10, Challenge Problems, where we're going to look at 7 or 8 problems that have to do with the idea of uh, externalities, more so government intervention. So let's go ahead and jump into it. Here's our first problem. And we have a chart table that lists the quantity, the private value, private cost, and social value. So the first thing that you want to do is kind of recognize that the private value is the demand curve. The private cost is the supply curve. The social value is going to be the demand curve plus the subsidy. So that's shown here in this particular chart. So the question asks, how large would a subsidy need to be in this market to move from the equilibrium level of output to the socially optimum level of output? So the first thing we want to do is to take a look at, well, where is equilibrium in the market? And we can see that we have a demand and supply that are the same here. So the quantity of equilibrium would be 4 units. Okay, so the price equilibrium is going to be 18 units, or 18. And then to the socially optimum, well, if we look right across here, the socially optimum is right here at 20. So if we take the social value of $20, we subtract the equilibrium price of 18, the subsidy would need to be $2, or answer C here, to move to the social optimum level of output. Okay, let's go continue to our next problem. Okay, so here we have, again, first thing to recognize, private value is our demand, private cost is our supply, and here we have an external cost. So this could be a tax in the market. And we need to figure out which of the following statements is correct. But the first thing I always like to do is to kind of get what is our supply with the tax. So I'm going to go ahead and add that in. So we would have 20 and 22, 24, 26, 28, 30, and 32. Okay, so, okay, cool. So now let's take a look at our statements. If the external cost per unit were nothing instead of 4, then the socially efficient quantity of output would be 5 units. Well, if the external cost is nothing, then we're going to go to equilibrium, which is where we have the 22 and the 22. So no, it would be 4 units, not 5, so that answer is incorrect. A tax of $8 would enable this market to move from equilibrium quantity of output to the socially efficient. Okay, so what is the socially efficient? Well, we can look right here and we can say that the $4 tax does, in fact, give us that socially optimum. But the socially optimum that we see here is where the private value of 24 equals the supply, or the social optimum level, or the private cost plus external cost. So that would actually be at 3 units. So if we increase that tax, that's not going to work because the social optimum is 3 units. So that also is incorrect. I'm going to taking the external cost into account, which we did here when we made this column. Total surplus declines when the 4th unit of output is produced and consumed. So let's take a look kind of at this. So if we look at, once we're at the 3rd unit, we can see that 24 and 24 matches, 26 is greater than 22, 28 is greater than 20. Excuse me. It's only after the 4th unit where the social optimum level, the private cost plus the internal cost, is greater than the private value. So here the I'll put it, the supply with the tax is greater than demand. So therefore, we know because of that, total surplus is going to be declining. So this is going to be the right answer. The market for flowers is a market to which, okay, no, that's just a, no, so not the right answer. So hopefully that makes sense to you. If it doesn't, again, please always let me know, and we can look at some other problems as well. Okay, so here we have another table. Again, first thing to recognize, private value is demand, private cost is supply. Here we have an external cost, so this is going to end up being a tax on the suppliers in the market to move us to socially optimum. Again, the first thing I kind of like to do is to get an idea of adding these two together. Where are we at? So we have 27, we have 30, we have 33, we have 36, 39, 42, and 45. Okay, it says, take into account, we just did that by creating this new column here, and assume that the quantity of output is always a whole number. The maximum total surplus that can be achieved in this market is how much? So the first thing that I want to do is to look at where is the private value equal to my new column that I've created. It's pretty close right here, and that's why they told us it's going to be a whole number. So this tells me that 5 is our social optimum quantity. So if we look at this, we can say, okay, so how much surplus do we have prior to that? So we're going to take the private value minus the new column we created. I'll call it the social cost column, minus the social cost, and that's going to give us the surplus. Okay, so for the first unit, we have the private value of 46 minus the social cost of 27. That's going to give us 19. Second column, 44 minus 30, and that's going to give us the 14. 42 minus 33, and that gives us 9. And the 40 minus the 36, and that's going to give us 4. And if we total all of those up, we end up with 46. So the total surplus, maximum total surplus that can be achieved is $46. Okay, so this particular problem, number 4, is one of these where it's intuitive to me. So I always have to slow down and make sure that I'm explaining it well. Here we have a chart that shows the marginal cost for each of firm A, B, C, and D to eliminate pollution. And what we're going to do in this scenario is we're going to, I'm grabbing something because I'm going to need it here in a second. Okay. All right, so what we're going to do is we're going to use the answers to determine how many units of pollution we can eliminate and how many units of pollution that will remain. So here's our marginal cost. We want to go from 16, and if you count the cells in this particular table, you're going to see that they equal 16. So this is the current state, to exactly 9 units. Okay, so which of the following would achieve this goal? So this is really a cost-benefit problem. So at $74, if the cost is less than that, we're not going to line it out. If it is greater than that, we're going to line out the cost. So let me show you on A what I mean. 54 is less than 74, so we're not going to line that out. 57, 54, 62, all of these are going to remain. We're going to line out 82 because it's greater than 74. Okay, so at 74, we have eliminated 8, have been eliminated, but we still have 8 units of pollution that remain. Okay, let's try the 85. So I'm just gonna, oops, sorry. Just gonna get rid of these real quick. All right, so now at 85, we're gonna go through our chart and do the same thing. So at 85, we're gonna eliminate this one, and obviously these 4. So when we look at this particular chart, how much pollution remains? 4, 8, 10. So we have 10 units of pollution, and we have eliminated 4, 5, 6. So we've eliminated 6, have been eliminated. Okay, let's do the next one. And again, for illustrative purposes, I'm going through each and every one of these because sometimes it's hard to wrap your mind around these. 87, all of these remain, all of these remain. 86 remains, 91's out, and anything above that is out. So how many units of pollution do we have? We have 8. Should I get this right? 8, 9, 10, 11. So 11 units of pollution, and that means that 5 have been eliminated. Okay, let's do our last one. Again, gonna erase that so that we can keep track of where we're at. Okay. And at $70, everything less. Okay, here we have 1, 2, 3, 4, 5, 6, 7 of units of pollution. And we have eliminated 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, that looks like the right answer because it is. We've eliminated 9. We still have 7. So again, wanted to reduce the pollution from 16 units to 9 units. So the amount of the reduction in this case would be the 9 that we eliminated. The wording of the problem also doesn't really, I think, help further understanding of this particular, how you work it out. Okay. Very similar problem. Give it a whirl and see. Again, you might want to pause and then check your answer with me. So I'm just going to walk through it step by step. Okay, at 84, again, everything less stays. Anything more goes away. So at 84, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 10. 10. And I have limited 1, 2, 6, right? Gotten rid of 6. Okay. Let's take a look at the next one. Because that doesn't seem to match our goal here. Because we want to get down to 5 units. Okay, so let's take a look. 87. Those all remain. That remains. That remains. Okay, notice wants to reduce pollution from 16 to 5 units. So there's our 5. We eliminated 11. So what would be the actual price of achieving this goal? 87. Now again, it's a little counterintuitive when we talk about reduction and the way I attack the problem. It might be counterintuitive, a little backwards, but it will get you to the right answer amongst the group. Okay, let's go ahead and look at, I think it might be our last problem, maybe not. So here we have the quantity, private value, private cost, again recognizing private value is demand, private cost is supply. We have an external benefit, so that's going to be the demand, socially optimum, or the, what do we call it, the private value, public value, right? Okay, so what we want to first do here in this particular example is look at our problem, private and external benefits. So what I'm going to do is to create my new column here. Let me get to the right sheet because sometimes I can look at these and go, this is what it is, and then I have to explain it to you. So I always try to make sure I do that well. Okay, so what we're going to do is we're going to add the private value with the external benefit to get a new column over here. So we have 32, 30, 28, 26, 24, and 22. Okay, the total surplus to society at the socially efficient quantity is how much? So we want to find the social efficient quantity. And if we look at the social efficient quantity, we can see that the private cost here and the external value are the same at 24. So that would be a quantity of 5. Now what we want to do is at any quantity less than 5, we want to add up the social benefit and subtract it from the private cost. So for our first unit, it's going to be 32 minus 12, which gives us 20. For our second unit, it's going to be 30 minus 15, which gives us 15. For our third unit, it's going to be 28 minus 18, which gives us 10. And for our fourth unit, it's going to be 26 minus 21, which gives us 5. If we add all those together, we're going to get $50 as the total surplus at the socially efficient quantity. Okay. Here we have more of a scenario type problem. I'm sorry, it wasn't our last problem. I think this one is. Maybe. Don't quote me. Okay. Suppose that company A's railroad cars pass through farmer B's cornfields. The railroad causes an externality to the farmer because the railroad cars emit sparks that could cause $1,500 damage to the farmer's crops. There's a special grease that you can put on there to eliminate those damaging sparks, and that grease costs $1,200. Suppose that the farmer has the right to compensation for any damages. Assume there are no transaction costs. Which of the following characterizes the efficient outcome? Okay, so basically what we have is the railroad and the farmer. Okay, when the railroad comes through, it could, right, emit $1,500 worth of damage, okay, to the farmer. Or it could buy this $1,200 grease to stop that from happening. So that's our situation. So they can spend $1,200 or they can spend $1,500. But if they cause sparks, then they're going to have to pay damages to the farmer of $1,500. So that's kind of the scenario that we're looking at, the cost benefit here, looking at each person individually. And we kind of want to look at which side we're talking about by the answers. So the railroad will continue to operate, but it will pay the farmer $1,500 in damages. Well, from the railroad standpoint, that seems like a stupid thing because we're going to take the chance, but we may have to pay $15. What if sparks happen every single day? That could be very costly, very quickly. Plus, $1,500 spending that is greater than the $1,200. So I'm not loving that answer. The railroad will purchase the grease for $1,200 and pay the farmer nothing because no crop damage will occur. To me, from a railroad standpoint, that is a clear what you want to do. If you're spending money, you want to spend as less money as you can, particularly in business. Here, that's going to preclude any type of compensation going to the farmer because you're not going to have the spark. So in this, I like B so far. It's my favorite, okay? The farmer will incur $1,500 in damages for his crops. Maybe, maybe not. It only depends if they could cause a spark. It doesn't say that that's going to happen, but it could. So therefore, I'm going to say, no, we're not going to pay for his crops, because then why would we even be in business, right? A farmer will pay the railroad $1,200 to purchase grease. Now, some people might say, if you're using the Coase theorem, you might have went with this one. Okay, but here's why B is a better answer than D, and this is why. Okay, causes the externality, there's a special, the grease cost. Suppose that the farmer has the right to compensation, and that the railroad cars have the right to be there. So in this case, the Coase-like situation would be for the railroad to purchase the grease to ensure that the crop damage doesn't happen, and that would be a more Coase-like advantage. Why would the farmer not pay for the grease? Because the railroad has the right, but the farmer also has the right, and in this case it would be damaged property, which is more of a legal right than the what if sparks come off from the railroad. So B is a better answer than D.